Hi, welcome to our next webinar, this on curved mirrors. Curved mirrors are a close analogy to thin lenses. They're an application of reflection, much like thin lenses are an application of refraction. In this, information on this can be found in your textbook. This just helps illuminate the topics, no pun intended, as well as notes for this may be found online on your website under the mirrors and lenses. Looking at a curved mirror, it is a segment of a sphere, typically speaking. They can be ground down differently. However, the basic idea is if you're looking at the inside of a mirror, a concave mirror, the reflective surface is on the inside. It can invert images, it can magnify images. One of the thoughts is these actually, unlike lenses, however, concave mirrors are converging. Convex mirrors, the reflecting surface is on the outside, as we see over here. They tend to spread light out. Convex mirrors, on the other hand, are diverging. Let's look at some mirror terminology. First of all, we want to look at the idea of the center of curvature. It's the exact center of the sphere, and the principal axis passes directly through this, and the principal axis is actually perpendicular near the center of curvature. The focal point is where light rays coming from an infinitely distant point, being parallel rays, will bend back onto the focal point. The focal point happens to be half the center of curvature. The third thing we look at is the focal length. It is simply the distance from a mirror to the focal point. It's positive on the object side. This would be converging mirrors, or actually concave, and it's negative if it's on the far side, diverging mirrors or convex. Finally, the object height is the same as what we saw. The image height and object heights are the same as what we saw in lenses. Simply how high they are, typically we'll say inverted images are negative. We're now going to use ray diagrams to locate our image. These are very similar to the ray diagrams that you saw for thin lenses. In this case, we're going to look at the example of a concave converging mirror. We want to remember the first principle that we remember is that rays that come in parallel will bend through the focus. Just as because light rays are reversible, a light ray coming in backwards will bend back through the focus, so a light ray leaving the head, that leaves the head of the penguin, goes through the focus, comes out parallel, as we see in the second diagram. One thing to mention, it may look a little strange, but for all of these, how they're defined, the center of curvature is perpendicular, the normal, the angle of incidence equals the angle of reflection for all of these mirrors. The third ray, because this is the center of the curvature, and from the center of curvature, a radius enters up perpendicular at any point. Let me just draw this perpendicular. Therefore, a ray that passes through the center of a mirror comes right back the way it came and comes backwards. This is not unlike the idea a ray passing through the center of the lens does not bend. We take our three rays and we combine them together and we can locate our penguin. We'll practice rules for diverging mirrors or convex mirrors tomorrow in class, but the principles are the same. Our lens equation, our mirror equation, is identical pretty much to the lens equation. Of course, on your AP assignment sheet, instead of D, they use S. We use positive focal length is converging, meaning concave mirrors. Negative focal length over here is diverging, meaning convex. Object distance, positive is real, negative is in back. Image distances, positive is real, negative is virtual. Upright things are positive, Negative ones are negative. Positive, again, being the good things. We can apply this exactly like we applied the equations of for lenses. An interesting fact is, how do these equations apply to plane mirrors? We remember that a plane mirror has a focal length of infinity. In other words, it's flat. The radius is infinite. Plane never curves, so an infinite focal length. So 1 over di equals 1 over infinity on a plane mirror. We solve for algebra, and do equals negative di. This tells us that if we place an object 4 centimeters from the mirror, the image will be a virtual image, negative. That's exactly the equal distance behind the mirror, negative 4 centimeters. So it works. If we think about the magnification of a plane mirror, the objects are reversed, but hi over ho equals negative. Now I'm going to make a substitution here, and I know that this negative is negative do over, I'm going to substitute for di over do. So the magnification of a plane mirror means that when you look into one, this all solves to 1. Thank you. In other words, if you're wondering why it's plus 1, the object is reversed, but of course it is not flipped over. Anyway, thank you very much. We'll have a great opportunity to practice ray diagramming when we do our mirrors lab.